Have you ever really stopped to wonder how an AI learns? You know, how it figures out how to recognize your face, or translate a language, or even drive a car? Well, it's not magic. It's actually math, but it's math inspired by biology. So in this explainer, we're going to peel back the layers and see exactly how these artificial neural networks go from knowing nothing at all to being incredibly smart. Okay, let's just dive right in.
To really wrap our heads around this, we're going to follow a pretty clear path. We'll kick things off with the OG blueprint, the human brain. Then, we'll see how we build a single artificial neuron and how those neurons team up to form powerful networks. After that, we'll uncover the really clever trick they use to learn. And finally, we'll see how this all kicked off the deep learning revolution we're living in today. You know, if you want to build an artificial brain, it probably makes sense to start with the original, right? That incredible processing power that you've got right between your ears, that's the blueprint for all of this.
So on the left, he's got a biological neuron, and on the right, its digital twin. And that resemblance, it is absolutely not a coincidence. The entire field of neural networks is basically a direct attempt to copy the brain's most fundamental building block.
See, in our brains, we have billions of these little guys. The dendrites, they're like tiny antennas, always picking up signals. The cell body processes all those signals, and if the message is strong enough, zap, the axon fires, and it sends that message on to the next neuron. It's this beautiful, simple system of receiving, processing, and passing information along.
So, how in the world do we get from that beautiful, messy, living cell to a clean piece of code? Well, let's meet the fundamental building block of an artificial neural network.
This right here is called a perceptron. It's pretty much the simplest version of an artificial neuron you can get. It's got inputs, kind of like the dendrites, and it's got an output. But the real magic happens in the middle. It uses math, specifically these things called weights, to decide how important each input is. Then it uses functions to make a final call.
The process itself is really logical. First, the perceptron gets some data. Then, for each piece of data, it multiplies it by a weight, which is really just a number that represents how important it is. It adds up all those weighted inputs, and then, and this is the key part, it runs that total sum through something called an activation function to decide if it should fire and what it should say.
So here's the crucial takeaway. This simple little calculator is the granddaddy of today's most powerful AIs. Yeah, everything from ChatGPT to Midjourney is basically built on the superpowered descendants of this one fundamental idea.
Okay, theory is great, but let's walk through a super quick example to really see it in action. So imagine our neuron gets 3 input signals with these different values. Each signal has a weight assigned to it, which kind of dials its strength up or down. We also add this little thing called a bias. You can think of it like a thumb on the scale, just to help fine-tune the final result. And then we have a simple rule, our activation function, that's going to make the final decision.
All right, here's the math. It's pretty simple. First, the neuron just multiplies each input by its weight. So 2 times 3, 5 times 1, and so on. Then it just adds up all those results, plus that bias we mentioned, to get one single number. In our case, after you do all the math, the combined sum is 8.5.
And now for the final step. We apply our rule. This particular rule is super straightforward. It just says, if the sum is a positive number, that's our output. If it's negative, the output is just 0. And since 8.5 is positive, it passes right through and becomes our neuron's final signal.
And that's it. That's the whole job of a single neuron. A few numbers go in, a little bit of math happens, and one number comes out. Simple, right? But what happens when we start connecting millions of these things together?
So that was just one lonely little neuron. But the real power, both in our brains and in AI, comes from teamwork. So let's see what happens when we connect these neurons together to build something much, much bigger.
By linking up thousands or even millions of these simple perceptrons together in layers, we create what's called an artificial neural network. The output from one whole layer of neurons becomes the input for the very next layer. This layered structure is what allows the network to learn incredibly complex patterns.
And the architecture here is really key. The input layer is just the raw data. Think about it like all the pixels in an image. The output layer, that's the final answer, like cat or dog. But all those hidden layers in between, that's where the magic happens. They're the ones identifying things like edges, then shapes, then textures, and combining them into a sophisticated final guess.
Okay, so we've built the structure, we've got our network, but when you first turn it on, it's just a bunch of random weights. It's totally clueless. It knows nothing. So how does it actually learn?
Well, the network starts by just making a guess. In this case, based on all its initial random weights, it calculated an output of 0.76. But let's imagine for a second that the correct answer was actually 1.0. That difference, that little gap between its guess and the actual truth, that's what we call the error.
And this right here is the most important question in all of machine learning. The network is wrong. How do we teach it to be less wrong the next time it sees this? You can't just tell it the right answer. You have to give it a way to teach itself how to find the answer. The answer is this incredibly clever algorithm called gradient descent. Its one and only job is to figure out exactly how to nudge every single weight in the entire network just a tiny, tiny bit in a direction that will make the total error smaller.
This visual makes it so easy to understand. Just imagine your total error is how high you are on a mountain, and you need to get to the very bottom of the valley, but it's super foggy. You can't see the whole landscape. But what you can do is feel which direction is the steepest way down from where you're standing. Gradient descent just does the math to find that steepest downhill direction, and then it tells every weight in the network, hey, take one little step that way.
This entire process, calculating the error at the very end, and then passing that error information backward through the network to tell each and every weight how it should adjust, that whole cycle is called backpropagation. You do this thousands, millions of times, and those initially random weights slowly get nudged into a configuration that produces amazingly accurate predictions.
All right, so we've seen the neuron, we've seen the network, and we've seen the learning process. So now let's just take one final step back to see how this all fits into the bigger AI picture.
So when you hear people throw around the term deep learning, all it really means is using these artificial neural networks we've been talking about, but using ones that have lots and lots of those hidden layers, which makes them deep. It's a really powerful technique inside the field of machine learning, which itself is just one part of this much broader quest for artificial intelligence.
So you see, AI isn't some unknowable, magical black box. At its very core, it's a system that was inspired by our own brains, built from really simple mathematical units that just has a very clever way to learn from its mistakes over and over and over again. And that leaves us with a pretty fascinating thought. Now that we understand how to build machines that learn, the biggest question isn't really how they learn anymore. It's what we choose to teach them.